Alright guys, let's talk about lesson 1, which is types of bonds. So remember, up to this point, we've been talking about atoms and electrons and how they are arranged on the periodic table, and that's been leading us up to where we're at right now, which is bonding. Remember, atoms want to bond. So what is a bond though? A bond is an intramolecular force that hold one atom to another in a compound. So it is the attraction or the intramolecular force. It's that force that's holding those two atoms next to each other. Now, in order for this to happen, energy is required. So the energy that is stored in these bonds is called potential energy. So why do atoms bond? We've talked about this before, so this should just be a review for you. Atoms bond together to get 8 valence electrons to become stable. Remember that stable octet. Now there is one exception, and that exception is hydrogen, because hydrogen can only have 2 valence electrons, and that's what we're going to call it a stable duet, because there's only 2. So forming a bond. When you form a bond, energy is released, so we call that an exothermic reaction. Exo meaning to leave, thermic meaning heat, so it's a release of heat. And this happens spontaneously on its own. And when this happens, when we form a bond, it forms a stable compound. So down here we have an example. We have chlorine gas right here and sodium metal right here. When these two come together, they make sodium chloride or table salt, and that releases an extreme amount of energy in the form of heat and fire. Now the opposite is going to be breaking a bond. When you break a bond, you are absorbing energy because it requires you to put energy into the thermic in order for the bond to actually be broken. So endo meaning in, thermic meaning heat. You're putting heat energy in to break the bond. Look at this little picture that we have down here. We have these molecules and we're adding energy into these molecules, and in do so we're breaking the bonds. When we do this, the stability decreases because now we're making things that are unstable. And an example, like we said before, an example of this would be ripping atoms apart requires energy. If you were to rip anything apart, a piece of paper, crack a pen in half or a pencil in half, you have to put energy in order for that to happen. So let's look at a practice problem. Which statement best describes the energy change as bonds are formed and broken in this reaction? So if we look at this reaction, we have hydrogen plus diatomic hydrogen plus diatomic chlorine producing HCl. So we are forming bonds, so it either has to be A or B or C or D. Now what I want you to do is pause the video, take your best get, and then unpause when you are finished. All right, welcome back. What did you come up with? Like I said before, we are forming bonds, so that should get us either to A or B. So when you form a bond, energy is released. So your answer here is answer A. The forming of the HCl bond releases energy. So that would be the best way to do this. All right, let's continue. There are 3 types of bonds that we're going to talk about in this section: ionic, covalent, and metallic. So we're going to talk about each of them one by one. Make sure you're filling out your note packets as we go through this. So ionic bonds is the first one. This happens when a metal bonds with a nonmetal. Something from the left side of the staircase bonding with something from the right side of the staircase on your periodic table. And the reason why this happens is that we have a transfer of electrons from the metal to the nonmetal to form a bond. So what does that look like? That happens because of why? We are always wanting to get this full octet. Metals would rather lose their valence electrons to be stable and have a stable octet, while nonmetals want to gain those electrons that the metals give off, and they'll become stable octet. So remember, when we're looking at electronegativities, this is huge. If you have something from the left side of the periodic table bonding with something from the right side of the periodic table, you're going to have a very, very, very high electronegativity difference. If you have a very high electronegativity difference, these atoms are not going to be sharing these electrons the same. One of the atoms is going to want the electrons more. And so that's where we're going to get an ionic bond. So let's look at sodium reacting with chlorine. We draw the Lewis dot diagram for sodium, we have one dot around Na. When we draw the Lewis dot diagram for chlorine, we have the one dot around chlorine. So what happens in this case is sodium's like, okay, chlorine, I know you only need one electron because this guy down here does not have a friend. I don't want this lone electron. He's getting on my nerves. So I'm going to give him to you and become a plus ion. And chlorine's like, okay, thank you. I'll take that extra electron and become a negative ion. Now these two, the sodium ion and the chloride ion, are going to have what we call an electrostatic attraction. They're going to be like two magnets that are going to be stuck together. They're both going to be stable because they are both going to have full valence shells, stable valence shells. They're both going to look like noble gases, and they are going to be happy. So let's look at the electron configurations, just where the electrons are in the rings around the nucleus. This is off of your periodic table in your reference packet. So sodium will give this one electron, so it will now have the electron of 2,8. Chlorine will take that one electron, and the chloride ion will now have the electron configuration of 2,8,8. Both of these are stable configurations. They are happy. They will be next to each other because that attraction, the overly negative chlorine, will be highly attractive to the positive sodium. So what does this look like when we're talking about electronegativity difference? Now, electronegativity difference from here on out, we are going to abbreviate as E.N.D. So elements in ionic bond have an electronegativity difference of greater than 1.7. So if we were to look at sodium chloride, for example, sodium has an electronegativity of 0.9, chlorine has an electronegativity of 3.2, so their electronegativity difference is 2.3. Since 2.3 is greater than 1.7, we definitely have an ionic bond. These electrons are not being shared evenly at all. Chlorine wants it and takes that electron away from sodium to make both sodium and chloride stable. Covalent bonds are a little bit different. Covalent bonds occur between two nonmetals. So these are going to be two elements that are going to be on the right side of the periodic table. And what they do is that instead of one element in this bond being highly electronegative and wanting electrons so bad that it will take electrons from a metal, they are going to share electrons to obtain a full valence shell. Again, why do covalent bonds happen? Covalent bonds happen because these two nonmetals want to have full valence shells so that they can become more stable. So what do? Instead of the one element being strong enough to rip the electron away from the other, they just share their electrons. Now, this is an easy trick to remember the difference between covalent and ionic. Remember the trick. Sharing is caring. Covalent begins with a C. Covalent atoms share their electrons. So why do they share instead of transfer? Each element does not have a strong enough electronegativity difference to remove or steal an electron from the other. So what they end up doing is they just share between the two nuclei those electrons so that they can become stable. So electronegativity difference, so elements of a covalent bond have an electronegativity difference of less than 1.7. So for example, if we're looking at carbon monoxide, CO, carbon, if you look at its electronegativity difference on your table 7 in your periodic table in your reference packet, and O, if you take the difference between those electronegativity values, you'll get 0.8. 0.8 is less than 1.7, so it is going to be a covalent bond. Another example is going to be hydrogen. Now, hydrogen, when hydrogen makes diatomic hydrogen, which is H2, since their electronegativities are the exact same, they're actually going to be in what we like to call a tug of war, an equal tug of those electrons, so that when they make that covalent bond, no one electron or one atom is pulling more than the other. Those electrons are being shared completely evenly. Now, there are different types of covalent bonds. The first one is a nonpolar covalent bond. A nonpolar covalent bond is when we have an equal sharing of an electron. That happens when your electronegativity difference is between 0 and zero point 0.4. This usually happens when the elements are identical. When we're talking about things like hydrogen and hydrogen, or in this example, chlorine and chlorine, or fluorine and fluorine, things like that. That's when we're going to get a nonpolar covalent bond. You have those electrons are being equally shared between the two atoms. So when we look at it pictorially, that's what this is going to look like. The black dot is a nucleus here. That's a nucleus here. And this blue region is the electron clouds that are being shared evenly between those two nuclei. A polar covalent bond is when you have an unequal sharing of electrons. So this is when you have an electronegativity difference between atoms that is 0.5 and 1.7. What this means is that one atom is slightly more negative and one atom is slightly more positive. And this is what we call a dipole. So what will happen here is that when we look at this, we'll have a partial positive charge and a partial negative charge. So when we look at this example up here of hydrogen fluoride, hydrogen here is going to be partially positive, and fluorine over here is going to be partially negative. Why? Fluorine has a really, really, really high electronegativity. Remember, it has the highest electronegativity of 4.0 on the periodic table. So it really wants electrons really bad. So what it's going to do when it forms this covalent bond is that it is going to pull more of the electron density towards it, and that's how we get this dipole. Again, we have the partial positive here where the hydrogen would be, and this is going to be the negative part here where the fluorine, or in our example, this chlorine would be. They behave the same way. So let's look at comparing ionic and covalent bonds. We can have nonpolar sharing, which is atoms are sharing electrons evenly. We can have polar sharing of covalent bonds, which means that the electrons are not being shared evenly. I like to also think of this as that you have an electron hog. You have something that really, really, really wants electrons really bad. Or you can have an ionic bond, which is going to have that electrostatic attraction between the positively charged metal and the negatively charged nonmetal. So let's do a summary of these bond types. So we have things that are ionic, and if they are ionic, they're going to have an electronegativity difference greater than 1.7. If they're covalent, they're going to have an electronegativity difference between 0 and 1.7. But remember that covalent could be completely equal, which would be nonpolar, and that would range from 0.0 to 0.4, or polar, where you're going to have that electron hog, that one element that has a high electronegativity that wants to pull those electrons away from the other one. And that would be when you have a covalent bond between two nonmetals that has an electronegativity difference of 0.4 to 1.7. Those are ionic and covalent. Now let's talk about metallic. Metallic bonds are different. Metallic bonds happen between metals in atoms of the same element. So we have all the same metal atoms here, and remember, we have those free moving electrons between all of those atoms. So look at this practice, and we're going to figure out which formula represents an ionic compound. So what I want you to do is I want you to pause the video, answer this question, and then we'll come back to it. All right, great, welcome back. So which formula represents an ionic compound? What I want you to do is when you're looking at these, you're looking for the one that has a metal and a non-metal bonded together. So when we look at A is two nonmetals. H, remember, hydrogen's a nonmetal, so that can't be it. This CH4 is also two nonmetals, so that can't be it. CH3OH is all nonmetals again, so that can't be it. So your answer is D. Calcium, Ca, is a metal. Chlorine, Cl, is a nonmetal. So that would be your correct answer for this practice problem. Let's look at a different one. The bond between hydrogen and oxygen in a water molecule is classified as what? Covalent and nonpolar, ionic and polar, ionic and nonpolar, covalent and polar. Pause the video, answer the question, and then we'll be back. Welcome back. We're looking at a bond between hydrogen and oxygen. Hydrogen is a nonmetal, oxygen is a nonmetal, so you're looking for one of the answers that has covalent in it. So it's either going to be A or going to be D. Now here's the question. When you're thinking about its electronegativity difference, do oxygen and hydrogen have the same electronegativity, or is one extremely higher than the other? So when we're looking at this, they do not have the same electronegativity difference. So it can't be A, because that means that they would share electrons evenly, and they don't. This is actually an example for a covalent polar bond. Oxygen is an extreme electron hog and wants electrons more than hydrogen does. So this is going to be an unequal sharing of electrons. So it is a D covalent bond. That is polar. All right, guys, here's your check your understanding that we're going to talk about tomorrow in class. The electrons in a bond between two iodine atoms are shared A, unequally, resulting in the bond that is polar, equally, resulting in a bond that is polar, unequally, resulting in a bond that is nonpolar, or equally, resulting in a bond that is nonpolar. Answer this to the best of your ability, and we'll talk about this in class tomorrow.